Hello students, this is our fourth lecture considering storage architectures. This is the last lecture of our third module that wherein we were dealing with the entire memory hierarchy. So over the past couple of lectures we were looking at the flash memory and the SSD controller, various functions that it has to perform. Today we are going to look at the last couple of functions. The first one is disk cache. So to understand disk cache, let's look at the entire memory hierarchy and look at the access time from the processor perspective. So if we have the x-axis to mark the access time, registers we can access within few picoseconds. Following that, if we need to access the first level of cache, we would need couple of nanoseconds to get the data back to the processor pipeline. If we miss in L1 and if we find the data in either the second or third level or even the fourth level of cache, typically we would need tens of nanoseconds of time to get the data back to the processor. Now, if the data is a miss in all the cache levels, we will access the DRAM and it would require a couple of hundreds of nanoseconds for the data to reach back to the processor. Now, if we miss DRAM also, it means we would need to access the secondary memory. If the secondary memory is based on flash technology, that's solid state drive or disk, we would need few hundreds of microseconds to get the data back to the processor. If we are using HDD, then we would require few tens of milliseconds, and if we were using a magnetic tape, it would take few hundreds of milliseconds. Now, just to put things in perspective, if our processor is ticking at 1 gigahertz, then 1 millisecond would be equivalent to 1 million cycles. So if we are accessing the hard disk, we would typically wait for tens of millions of cycles to get the data back. Now, in order to speed up things at the secondary level, the architects have come up with a more intuitive idea of disk cache. It is beyond the main memory and will be placed very close to the secondary memory. In fact, it's on the same PCB, you can say, or in the same module, and it's based on a faster memory technology. It can be an SRAM or a DRAM, and all the frequently used pages will be placed in the disk cache. If there is a data hit in the disk cache, we would need only a fraction of few microseconds to send the data back to the processor pipeline. That means we would get 100 to 1000 times speed up if a data request is hit in a disk cache when compared to the HDD or SSD. Like I have mentioned, disk cache is predominantly based on some faster memory technologies, usually DRAM. Few of the storage solutions offered by companies have SRAM in it. Now, by the time we reach the disk cache, we would have spent few hundreds of nanoseconds because we would have checked the main memory and it would have been a miss there. It means a page fault, and eventually we ended up accessing the secondary memory. But even at that point, if you are able to give the data back as fast as possible, there is a huge scope of performance improvement. That was the reason disk cache was earlier deployed in magnetic disks because the speed disparity was quite high. Now we are using disk cache even for SSD based storage too. There are a couple of reasons for it. The first one is the latency benefit. The second one is if the disk cache is able to absorb many of the writes from the processor, it would improve the lifespan of the SSD flash memory cells too. In addition, if we have a hit in the disk cache, we would also save the power to access the SSD. So it is a very simple and lucrative solution that the designers have used when they are proposing few storage solutions and products based on that. The disk cache is used by the controller to direct all the requests from the host. So whenever there is a request from the host processor for some data, the controller will first check the disk cache, and if it's a miss, then the request is directed to the flash memory cells. Apart from that, it will also note down what are all the highly used pages, frequently used pages, and it stores them in the disk cache. Here too, as you already realized, principle of locality is coming into play. All the frequently used pages or hot pages we can say are placed in the disk cache in a hope that in the future they will be reused again. The disk controller will also store the firmware which would have been in the ROM for again the faster access, and it would store any other metadata that it would be needing for smooth operation. Along with that, it will also store the mapping tables of logic blocks to the actual NAND blocks, the flash translation layer in the disk cache. Though disk cache has so many plus points, if we want to deploy a disk cache in the SSD, we need to make sure that there is an internal power backup within the SSD. Usually it's super capacitor based power backup. The reason being, upon a power failure, all the disk cache contents need to be copied back to the flash cells if it is the user data or the OS data you can say, and if there are any changes in any other metadata or the mapping tables or some variant of the firmware, it needs to write them back, which takes finite amount of time, and the SSD should be up and running during that finite amount of time for the entire copy process to happen. That's the reason we need an power backup. If we do not provide such a power backup, the moment there is a power loss, because the disk cache memory technology of either SRAM or DRAM, because it's volatile, it will lose all the data, and it can result in a corrupted data of the user or the firmware or the metadata. Typically, we would see around 1 GB of DRAM cache in the current SSDs. Now, even though we are having our regular systems with with 16 GB or 32 GB of DRAM, we have limited ourselves with less than 1 GB of DRAM cache in the SSD, primarily because the power consumption is high and there is a area limitation too, because the SSD should be conforming to some form factor. Along with that, the larger the disk cache, the more the contents will be. It would demand that it needs more time for the battery backup to be on. So these design decisions will determine the overall disk cache size. The disk cache itself will have a controller similar to what we have seen in the DRAM module. The DRAM has a memory controller. So here too you can imagine that there is a memory controller within the disk cache to manage its operation and communication with the disk controller. The disk controller, if it has a disk cache, can proactively write back the data whenever the host is not accessing the disk cache, so that the backup process happens quickly. So with that, we will move on to the last reliability and maintenance feature of the SSD, which is RAID. RAID. Reliability and availability of the data are important metrics for storage. We would want our data, whatever we have stored, to be available to us 24/7 whenever we want to access. Also, we do not want to lose the data. To address this demand of the users, the system architects have come up with a concept called RAID. It expands to redundant array of inexpensive disks. So inexpensive was used when when the storage solution was based on HDDs because they were very cheap, but SSDs are slightly costly. So instead of inexpensive, we can have independent disk. Redundancy can deal with one or more failures. And if you remember, redundancy was one of the great ideas of computer architecture that we have seen in module 0. In addition to providing a reliable storage, redundancy can sometimes help us with faster access of data. We are going to look at a couple of simple examples. RAID configurations employ techniques like striping, mirroring, parity, sum check, and error correction, so on and so forth, to ensure reliability of the underlying stored data. So typically each sector of disk, so the RAID was predominantly used when HDDs were the main storage technology, but it is still relevant in SSD framework also. So whenever you come across the term disk, you can replace it with a block of data, NAND block, or something similar of similar granularity. So each each block can itself have some error correction data. So there is already a little bit of redundancy in the existing disks. When we access the particular disk and when it reads the data, and if it finds that there is an error in the data, then we would need such redundancy techniques to get the correct data. So over the past few decades, we have many levels of RAID with improved capability and better deployment facilities. We are going to here is an overview. RAID 0, it doesn't have any redundancy, so there is no overhead with redundant check disks. So if we have 4 disks, all the 4 disks will be used for data storage. RAID 1 has mirroring capability, and what it means is if we have, let's say, 8 disks, half of the space is used as a copy of the data. So the blue disks would have the same data as this gray disks. RAID 2 is where we have error detection and correction facilities. So, and it needs 3 extra disks if we have a total of 4 disks of data. So it's almost 75% overhead. RAID 3 is bit interleaved with parity check, and to store the parity bits we need an extra disk. RAID 4 is an extension of RAID 3 with block level interleaving along with parity. RAID 5 is RAID 4 with slight change where the parity is not stored in a single place or the single disk, it is spread across all the 5 disks. RAID 6 is where we have a checksum feature along with parity. Accordingly, we need 2 extra disks to store the parity and checksum features along with our 4 disks of data. So let's look at each of these levels a little more in detail. RAID 0, like I have mentioned, it doesn't have any redundancy. So RAID is not the most appropriate term for this level, but it has been a standard practice to use it. So what RAID 0 does is it will use the array of disks to interleave the data across these arrays so that when we access a chunk of data, each of these arrays can give us a part of it. For example, if we have, let's say, disk 0 and disk 1 and the addresses are A1 to A8, in RAID 0 we would place A1 in disk 0, A2 in the second disk, A3, A4, A5, A6, A7 and A8 in such an interleaved manner. So each of these addresses can be imagined to be at block level. Now in case one of these disks fails, we are not going to lose all the data but only half of the data. That was the main selling factor for RAID 0. Also, let's say if we want to access data of locations A1 to A4, we will be accessing both disk 0 and disk 1 in parallel, and disk 0 will supply A1, A3 and disk 1 will supply A2 and A4. So we will be able to get this data in half the time. So by default, all our storage or the secondary memory is configured as RAID 0. The next level is RAID 1. What it does is it mirrors or shadows or copies the contents of one disk to another. So it means that there will be 2 copies of every data. It also implies, so for example, if we have 2 disks, disk 0 and disk 1, A1, A2, A3, A4 will be present in both disk 0 and a copy of them will be placed in disk 1. It also means that whenever we want to write to a location, let's say A1, we need to write to both disk 0 and disk 1 so that they are always coherent. Now, if we say that disk 1 is a mirror of disk 0, whenever there is a request from the host for any data, we would first check disk 0. In case we fail to get the data from disk 0 because of any disk failure, we would then go to disk 1. That is one aspect. Otherwise, to get a little better performance, what we can do is, if the host has requested for A1 and A2, we can send a request to disk 0 for A1 and disk 1 for A2. So again, there is a slight improvement with the throughput of data access. This is an expensive solution because even though it is providing a highly reliable framework, we would be spending twice the cost. The reason being, half of the storage that we buy will go for maintaining this copy of the data. So just to quickly relate, let's say you have bought a 4 TB external disk and you have configured it with RAID 1. It would mean that only 2 TB of it will be available for you. The other 2 TB will be having a copy of this. So which is pretty much useless. We would be spending money unnecessarily. That's the reason we have next levels of RAID which have improved on top of this. The next one is RAID 2. Here the data is striped at bit level, and along with this striping we would use error detection and correction code in case of any failure to get the data. So to store this extra information we need additional disks. So if we have our storage having, for example, 7 disks, in RAID 2 we would be using the first 4 disks to store the actual data and the remaining 3 disks to store their error detection and correction codes. So here, for example, A1, A2, A3, A4 are our data blocks, and AP1, AP2, AP3 are the corresponding codes which will help us to detect any errors and correct if there is any error. So it's slightly better in with memory usage when compared to RAID 1, but still the overhead is high. So just like RAID 1, it's no longer in use. After RAID 2 we have RAID 3 level, which stripes the data not at bit level but at byte level across several disks, and each disk maintains a parity information for this byte of data or a group of them. If you're wondering what parity is, it is the sum of all the data bits divided by 2, or the remainder is looked at. For example, if your 4-bit data is 1010, it would be added resulting in 2, and its modulo 2 would be 0. It means that there are even number of ones in your 4-bit of data. So it's called even parity. If the resultant is 1, we would call it odd parity. So in RAID 3, if we have, let's say, 4 disks, 3 of them will be storing the data and the 4th disk will be storing the parity of each of those blocks. So here the parity of A1, A2, A3 is stored in the 4th disk. And just as an extension, let's say if we have 8 disks, byte 0 will be in disk 0, byte 1 will be in disk 1 because it's striped at byte level. So the first 7 disks will have 7 bytes and 8th disk will have the parity of all the 8 bytes. Now if we want a block of data, let's say 64 bytes of data, what RAID 3 demands is we go and access all the disks to get the information. So it is better in one way because we are going to get the 8 bytes of information with the same time as 1 byte of information per disk because they are happening in parallel. But there is a downside. We're going to look at it just right after. Before that, a point on writes. If you want to write a new data, then we would need to access all the 8 disks. Sorry, there's a typo here. We need to read all the 8 disks, and we need to recalculate the parity and write it in the last disk. So we can get multiple bytes of data in parallel. So the throughput is high for a single request, or we can say latency is good for a single request. But if we have multiple such requests, they need to be processed in sequence. To reduce this overhead, RAID 4 develops on RAID 3 and proposes to stripe the data at block level. What it results is, if we want, the host wants a block of data, it can access one disk only, even though there are multiple disks, and the other disk can be used for some other parallel request. So the throughput will increase, but again, as you would have guessed, the time taken to transfer this block of data will be higher. Now, in case if we have any error in the disk read, then we would read all the disk and check the parity. The parity is maintained at block level in the separate disk. So in this figure we have 4 disks, 0, 1, 2, 3. 0, 1, 2 will be storing the actual data, and the fourth disk will be storing the parity at block level. So if we have an error in accessing, let's say A1, then we need to access A1, A2, A3, recalculate parity and compare it with the parity already stored, and based on the difference we can regenerate A1 to some extent. As I have already mentioned, block interleaving reduces or increases the latency for single request, but multiple requests can be processed in parallel. It's called task level parallelism. On a write, though, we need to access the the disk where the actual data is stored along with the disk where the parity is stored. It would mean that if we have back-to-back writes, all of them would need to access this disk, the last disk, and they can only be processed in sequence, in a serial fashion. Sorry. So upon a write, the parity information is calculated and it will be updated only if there is some difference, otherwise the original parity is continued. RAID 5 develops or addresses the limitation of RAID 4, which is limited because of back-to-back writes to the back-to-back writes need access to the single disk. So what RAID 5 proposes is, let's distribute the parity block also among all the disks. So in RAID 5, what we would have, for example, is A1, A2, A3 are stored in the first three disks, and their parity is stored in disk 3. Earlier this was the only case, but if you look at the next set of data, B1, B2, B3 are stored and in disk 0, 1 and 3, and now disk 2 has the parity. So the parity bits are distributed over all the disks. Now what happens with such an arrangement is, if you want to write to A1, we would need the parity information in disk 3, but if you want to write to, let's say, D2, we would need the parity information which is in disk 0. So the number of conflicts among multiple parallel writes will be less, so the write throughput will increase. So far what we have seen is the data being striped across multiple disks, and parity information being maintained in one of those disks. What RAID 6 proposes is the limitation of parity. Parity can help us to detect only single bit failures. But what happens if we have more failures is we need to provide some extra information. So we have RAID 6, which will provide the parity information at the block level. In addition, it provides a checksum feature in case the parity check is failing. So checksum is the sum of all the data that is being that is there, and that summed value will be written in a separate place. So upon a failure, again the data is summed, and if there is a difference, based on that difference the error can be identified. So if we have, let's say, 5 disks wherein the data can be stored, A1, A2, A3 are storing the actual data here, and the disk 3 is storing the parity of these 3 blocks, and disk 4 is storing the checksum of these 3 blocks. And just like RAID 5, RAID 6 also distributes the parity and checksum. So we have AQ in disk 4, BQ in disk 3, CQ in disk 2, DQ in disk 1, and EQ in disk 0. Accordingly, the parity information is also distributed across multiple disks for enabling parallel read operations and parallel write operations. So overall, our throughput will increase along with a reliable storage. So RAID 5 required one additional disk and RAID 6 when compared to RAID 5 would need another additional disk. Along with these RAID 0 to RAID 6, there are few other hybrid RAID levels, also called nested RAIDs. For example, we can have RAID 01, which is a combination of RAID 0 and RAID 1. What it does is it stripes the data and also mirrors them. Here, for example, if we have 4 disks, disk 0, 1, 2, 3, the data in 0 and 1 will be mirrored in 2 and 3, that is the RAID 1, and within these 2 disks the data is striped, which is RAID 0 feature. Similarly, we can have RAID 10, which is RAID 1 on top of RAID 0. So here RAID 0 says the data here in these 2 disks will be striped with these 2 disks. So we have A1, A2, A3, A4, A5, A6 here, and within these 2 disks the data is mirrored, that is RAID 1. So A1 and its copy A1 are within these 2 disks. So A2 and A2, so on and so forth. Similarly, there is a RAID 03 level, which is it would require at least 6 independent disks to be available. They are grouped in twos, and within the 2 of them the data is striped, but if you look at the 3 groups, the parity information is maintained in the separate disks. For example, here disk 4 has the parity information of disk 0 and disk 2 together. In the same way, disk 5 will have the parity information of disk 1 and disk 3. So similarly, we can have other RAID combinations, RAID 05, RAID 06. If you're interested, you can go through the link given on the slide. The wiki page has been quite descriptive, not only for this but even for the basic RAID levels also. So with that, we have covered the core of the storage architectures. Is related question is, we would access the storage whenever there is a page fault in the main memory, and we would bring in a page of data which is typically 4 kilobyte or 8 kilobyte of data from the storage to the main memory. Now it's not that we are transferring a word of data or a block of 64 bytes. We are transferring pages. How does that happen? If the processor is monitoring the transfer of such huge blocks or huge chunks of data across multiple memory levels, or it can be that you are trying to copy data from your external USB to your hard disk. How does the processor handle that? If it's monitoring every byte transfer, then it's a loss or underutilization of the processor resources, because all the peripheral circuits and the secondary memory and the main memory are much slower than the processor. To support such huge data transfers, a special control circuit is designed on the motherboard, and the technique or the method is called direct memory access. So there will be a DMA controller, direct memory access controller, along with the disk or any of the peripheral interfaces, which will be connecting to the south bridge, which manage the data transfer between the main memory and all the peripheral circuits. So here the bridge is a generic one. It can have, you can imagine it having both the north bridge and south bridge. Now to initiate or to signal the DMA controller, the processor needs to send 3 bits of information. The first one is the starting address or the starting location of the data to copy, the number of blocks of data to copy. Here the block, you can imagine, can be a 64 byte block, and it would also need to give the direction of transfer, whether it is from the main memory to the secondary memory or the secondary memory to the main memory. Once this information is present, the DMA controller takes over the accesses of the disk and the main memory and performs the transfer. And once the transfer is complete, it signals to the processor saying that a successful transfer has happened. So this is just a quick, very high level overview of how large transfers happen. The implementation details of DMA are quite mature, and given the related material, if you're interested, you can go through. Just wanted to give a quick overview here. With that, we conclude the storage architectures, and if you're interested, the current trend in the storage is to have multiple levels of memory within the storage. So it can be a combination of SSD and HDD. So many of you, the current laptops come with a huge magnetic disk supported with, excuse me, 128 GB or 256 GB of SSD. So you can imagine that the SSD itself is acting as a cache for the magnetic disk. SSD is usually termed in such multi-level storage as online storage, and HDD is for offline storage. Currently, the flash cell designers are exploring quad level flash cells, wherein we can store 4 bits of information in each flash cell. So this has been enabled both by the developments in the fabrication and the process technology. Apart from flash cells, there are few other non-volatile memory technologies that are being explored for storage. For example, magnetic resistive RAM, MRAM, is being explored by Buffalo company. Spin transfer torque MRAM, or STT-MRAM in short, is being explored by Everspin. 3D crosspoint is another NVM technology that is being explored by Intel and Micron. Among these, the 3D crosspoint based products are already in the market. So one popular product from Intel is Intel Optane memory. You can have a look if you're interested. It's not based on flash cells, but rather 3D crosspoint cells. There has been a significant improvement in the 3D integration of flash cells. Currently, we are able to stack 128 layers of NAND arrays, one on top of each other, to get better density. So as I mentioned that there are few other NVM technologies that are being explored, and it has already been found that these technologies are much faster than flash based memories, and they have better endurance capabilities also, which is a huge limitation of flash. They are being explored aggressively, and to support such fast storage elements, a new peripheral interface has been proposed, which is non-volatile memory express, NVMe. So the SATA or USB interface that we have been using so far is very slow for these NVMs. So NVMe is being explored. The last point is quite interesting, and it no longer follows the von Neumann architecture where we have a separate storage space and a separate compute space. Here the computation and storage happen to be almost at the same place. It's called processing in memory, wherein we are able to do some computation within the storage. If you remember, we have a mini CPU there, RISC processor. We can probably use the RISC processor in the storage itself to do some processing, instead of getting the data from secondary to the primary, then to multiple levels of caches, eventually to the registers, which is a very slow process. So PIM, processing in memory, is one of the currently hot topic people are looking at to speed up the overall application performance. So with that, I conclude module 3, and the reading assignment for SSDs is the SSD 101 ebook that I already shared. Along with that, today I'm going to share a few additional material that talk about write abort, read and program disturb concepts. If you're interested, you can go through. For RAID, I would suggest you to go through the CO and Design RISC-V edition by Patterson and Hennessy, specifically section 5.11. Along with that, a Wikipedia page was quite helpful for me, and I found it to be quite comprehensive. I would strongly suggest you to go through that page too. For DMA, I would suggest you to go through the introduction part of section 4.4 in Computer Organization 5th edition book by Karl Hemacher. So it's just a couple of pages. It will give you an overall idea of the implementation details of DMA. Next few classes, probably next 3 to 4 classes, will be moving on to the next module, which is improving the performance of the program with our overall understanding of the memory hierarchy. It will help us to become better programmers. I'll pause this lecture now. Thank you.